Okay. I think this should work. Now, where were we? Qwen3. So the goal is to generate the goal of this is script to load the Hugging Face Qwen3 and take the weights and put them in the same format as the params object for gamma. So the same format so that we're ready to start thinking about whether we put them right or wrong and so on, but they should just kind of fit in there and kind of work. So the next step will be to make it work, that it does something, and then later we will try to see if we modify it so that it then gives the same output as Qwen does for Hugging Face. But we start going slow because this is a bit of a big thing. So now I'm loading the parameters. I already have them here for gamma 3 as they work with the gamma code base, and I do not need to load the model. And with tree scope I can look at the dictionary, and then this is all stuff that I did in the last video. So I have then the Qwen model, I'm loading it, it will be cached locally when you do this from pre-trained, and then I have a model. I can take the embedding matrix that we use for the initial residual stream, and it's there, and I then turn it into a JAX. We found that I can use this kind of from DL pack, and then we see that the vocabulary size in gamma is 262k and this is 151k, and it has a bit of a smaller size in hidden dimension of the residual stream. And we found that we didn't actually find, did we find this? I do not remember. I think we concluded that there was not a final norm, layer norm in the Qwen, but that was before I started looking at the code base. So it's already, sorry to get distracted. Qwen GitHub. This is Qwen, and we concluded that it was Qwen2. It's the same architecture. Qwen2 decoder layer, this kind of stuff. Modular Qwen, and yes, the thing is we're not thinking that we'll get this far so far. So actually right now we should just be able to load in the matrix in E1, E in, and maybe like the first layer or something, and that's why we're focusing on the self-attention. So right now what I'm doing is I'm just saying the final norm scale for the RMS norm probably is going to be 1s, and then I'm putting in the embedder, input embedding. That's because this is the way it looks. Gamma's own parameters, they are a dictionary where there is one key that's called embedder, and inside there's a dictionary with an input embedding. And now I'm doing the same. I'm putting in my Qwen3, this thing, and I'm putting also a final norm. And they're B floats, that's good. They are also B floats, B float 16. and then we have a current layer. I'm taking the layer out of the Qwen model, and I'm saying let's look at the input layer norm. This is the input layer norm. In Qwen, you're using this input layer norm. Are we not? Am I getting confused now? Input layer norm. It's because this does not contain the whole thing. Mistral model. Okay. Qwen. Yeah, I have to move a bit fast because I was quite sure that this was what we concluded, that the input layer norm here can be like this, and the pre-attention norm is what in gamma is being used before everything. So we're in here in gamma, neural networks, transformer, and we have a bunch of stuff here, exists input embeddings, and then we start going with the blocks, and yeah. So where were we? We wanted to understand the attention and the KV einsum. The KV einsum was what we were now on to, and we have two matrices because we have a key and a value affine, no, linear transformation onto a dimensionality of this thing. Number of attention of the hidden size. So I'm now going to go into the layer, current layer, and to the self attention, and I'm gonna take out the K projection, and I'm gonna take the weight from it, and I'm gonna take the data, and then I am going to say this has some shape, and I'm going to concatenate it with the query, no, the value V projection, and I'm not going to use the shapes, of course. So like this, and I did not import torch. So that works, and that's called now layer S KV matrix torch tensor. And then I'm gonna pack it again, so I'm saying there was some name here for it, KV einsum. KV einsum is equal to jax.dlpack.from dlpack, this layer S KV matrix thing. KV einsum has a certain shape. It is not good because we don't want to concatenate them, we want to stack them like that, and then they have a 1, right? And that we can do something like kv sum is kv sum none, except if that means something else, of course. Not none, like this. But I'm not sure if this 1 is why there's a 1 there, if it's because of something about the current architecture that they map somehow. But I think it would make sense that we just have 2. So what is a kv sum dot shape 2 1? It's mapping to this, and we just want to make sure that they're both mapping from 1000. It's because this kv is for all the heads. Yeah, it's for all the heads. And we know that in gamma it's 256. We also know that it's 128 here. So we want to say eight. What? 8. Is there some kind of 8 up here? Number of key value heads. This is the number of key value heads per. And if we were looking at projects, git clones gamma, there was number of kv heads 1 here. So it might very well be that one. Might very well be that one. I'm very certain that it must be that one. So that means we should reshape it. And again, I'm nervous about this reshaping, but I also have to move a bit fast. So I think I will just say that we're gonna reshape there. We're gonna reshape it into two times this thing that we have here. It's called num kv heads times the hidden dim times the hidden dim times the not the number of attention heads, the attention size. Do we have to compute it ourselves, or do we have it head dim like this? This is what I believe it's meant to be. Number of key value heads. Oh. So this is what I believe is meant to be. The one that's called Qwen3. Qwen3 inside the attention dictionary is called Qwen3. And I'm gonna move this down here. And also this. And just a bit of stuff here. I just want to clean up a bit because I think I'm gonna get confused otherwise. This is then the embedder.input embedding, and this is the final norm.scale. And then we have for layer S, we're getting the S. What is this? This is QV projection. So this is called layer 0 dot attention dot Qwen3. In query heads, I would like us to not use so many variables, just rely a lot on this stuff. Well, like that. And then now we are in layer 0 dot attention dot Qwen3, and we're putting it all in. And we do not have key norms and query norms in Qwen, and now we have an attention vector einsum. An attention vector einsum which has 4, 2, 5 attention vector einsum. There. It is being used as the output matrix. It's the O projection thing. So it's the batch T N H coded. So we have 4 of them because we need one for each query, and we're going down and up. Yeah, and so we go down now in layer S, current layer dot self attention, and we have here a very nice one that we're gonna use. So it's an O projection dot weight dot data, and this is then checks the deal pack from deal pack, and this is the O projection layer as O prime, and from this layer as O prime dot shape, we are gonna reshape it so that we do not have just 1,000, but instead we have 4 of them. So we're saying reshape to use the number of key value, no, number of query heads, number of attention heads. Okay. And then what do we have? We have the hidden dim, the head dimensionality, and we have the hidden size. So we're projecting them up after we've used computed all the things. We're gonna project it up, and it worked well. And then we are gonna call this layer S. We're gonna call it attention vec einsam, and we're gonna move it down like this. Attention vec einsam. I just discovered. I wonder if I have been muted all along. Oh, let's just see. Live. I wonder if I have been muted all along. Attention. Attention vec einsam to layer as attention vec einsam. Great. And now we have that, so we have to go back here and say I have this and this and this, and this is actually, except for the pre-attention norm, which I already have, I kind of have everything that I would need in order to start using, trying to fit the forward pass in, but I think it will not take too much time doing the remaining ones. And once we have those, we have almost everything. So let's do the MLP. It has a gating sum, and some 2 of those, they map upward, apparently. So let's see. Tree scope.show. Gamma brands of layer 0, this one. we have a layer S that's called current layer, and in there we have some MLP, and we have a gate projection and an up projection and a down projection, and we're interested in this gating ensemble, which I talked about in the previous video, that we have these two. We're projecting upwards from 1000 dimensions up to 3000, and then we're applying a CELO activation function to one of them, probably this one, and then we are going to project down again after we added them. No, multiply. We will, yes, multiplied. Otherwise, yeah. Okay. So how do we do this? We say current layer dot MLP dot gate projection dot weight dot data, and then we are stacking that with the current layer dot MLP dot what was it called, up projection, and then we do not know if we have the right direction, of course, the right order, but at least we now have these two and they fit with this idea that the big one is up here and the small one is here. So this I'm gonna call layer S MLP gating einsam when I first use jax.deal stack, no, deal pack from deal pack, like that. So layer S MLP gating einsam, yeah, and then I'm gonna put that in here, gating einsam, and we're gonna move this one down, and we're gonna move this down, and do like that. Okay, so now once we have that, we can do this would be layer 0.mlp.gating einsam. Now we can do the linear one, which would be current layer dot MLP dot down projection dot data, no, dot weight dot data, and this we will just say it has the right shape, right? No, it should be transposed to have the big one first, like that, and then we will say jax.dlpack.from dlpack, and then we will have that being called the linear. Layer S MLP linear. Great. That would be like that, and it would go here. And now we have those two, we can go to the post attention norm. So we have a single normalization after that, and it would just be for the so it does not look like there's any post attention layer on there, and here we have the decoder layer. We have an input layer norm and we have a post attention layer norm, which is very good. So let's just take that one. Current layer dot post attention norm layer norm dot weight, no, dot weight dot data dot shape, and we pack that. Is it deal pack? That from deal pack, like that. Deal pack, and that would be called layer as post attention layer norm. I wonder if it is not layer norm, it is an arms norm, right? Yeah. Okay, so that goes directly into something called post attention norm. Post attention norm, they are wording it a bit better over at Google, and they put it inside something called a scale here. There, layer 0 dot post attention norm, the scale. Okay, and post feed forward norm. Post feed forward norm. We do not see anything, so we will just do, until we find better, a post and pre and everything. Is did I do something else where I did this? Just once like. Whoa. What happened? What is this? Debugger. Yeah. So just say layer S post FFW norm is just text at once like do ones. They're just ones. The hidden size, it's called. But the problem is, like, it's not. No, I will just do none. There will be none. And I'll just hope that you can actually do that. Post FFV norm, pre FFV norm. But all the others were underscore. Now this is the only one that is underscore, which is a bit worrying. But let's just try. Okay, so now I have all this. Oh, pre-attention norm. This is up here, but it's fine. Attention, key norm, Q1, KV, einsam, attention weg, einsam goes up here. It's just for good order, of course. Yeah. So now it's starting to look reasonable. Yeah. And what do we then do? Then we just go up here and tree scope the full one again, because it was indexed by layer and S. So we will say for S in range layers. Max window layers, what is this? Oh, number of key value heads, number of hidden layers. There. We will do Qwen config, model config. We will do this thing. So I'll make a function now. That's called def get params for layer. Current layer. This, and then I will be this, and I will, yeah, it's a bit of a weird way I did it here. Could also have looped over the layers in the model, but whatever. Layer S params is equal to get params for layer. And then I will take my, what will I take? I will take the dictionary I have here, and I will say that layer number S is equal to layer as params. And once I have done that, I will just show the Qwen gamma params. Qwen. Like that. Layer 0, blah blah blah. We have all these matrices. And it looks alright. Params, gamma params. And lastly, I will think about trying to avoid loading anything here. So can all of this code now run? It almost can. I just need to do this one. It's the hidden size. This is the hidden size. Great. Yeah. Because now I have at least something that I could try to load a model with if I wanted to. So I will just wrap all of this in some kind of function here. It's gonna be a bit bad, but we gotta move fast. So this is called Qwen gamma params. Qwen gamma params. My Qwen gamma params get print my keys. Great. And then I'm just gonna try to run it here. Not here, there. Part 3 make. What do we say here? Bam, bam, bam. Okay, this is sufficient for the goal of part 3. And now I'm gonna stop and just read and then do part 6, but I have to go to bed also. Yeah, this is it.